My name is Sumit. I have been working in the analytics industry since quite a few years now. I have a PhD in decision science from IIM Bangalore. Prior to that, I finished my BTech from IIT Dhanbad and was working in software engineer. I did my master's come PhD from IIM Bangalore, which was in the quants that's used in business, like statistics and operations research used in economics, finance, operations management, and all business field. And my work was on quantitative modeling. After that, I've been working with different companies where I have done work in the finance domain for the healthcare industry, in the telecom domain, and for commodities market, where my work has been to support the business in getting actionable insights through data. Let me take you one of kind of works that I do. So this session will go around time series analytics. I'm assuming that you have some basic knowledge of statistics, but if you're not, please feel free to tell me. I will discuss those topics in details as well. I'm also assuming that you have some basic programming knowledge, but there is no need for no for where when we do this lecture series in Lecteron, there's no need that you have to know maths or statistics or programming beforehand. In time series, the only independent variable is time. That's a very good observation, Jayashree. Later at the end of the class, when we are doing vector autoregressive models, remind me this line, because in that case this does not work, or vector error correction model. We will get there when we get there, but in generally a univariate time series, the only independent variable is time, and there is one dependent variable, like the amount of sales of Walmart on a given day across a year. That's a time series data. On day 1 of the year, on January 2nd of the year, January 3rd till December 31st of the year, how much did Walmart do in a particular area in, say, Fresno, or in Los Angeles or San Francisco? So that's a time series data. Another example could be the price of the stock market. It is there on every day. Another example could be the crude oil prices, the per gallon, what is the dollar rate that's going on. That's a time series data. The amount of rainfall in New York, the amount of snowfall in London, all these are time series data because they are time indexed. On any given day of the year, what is the volume or value of that price or volume of rainfall or things around that. Shiva says data which deals with time like monthly, yearly census, etc. Perfect, Shiva. Thanks a lot. I missed census. So the population data is a census data. What was the population of Washington State over time? That's a time series data. So here I have a small time series data. Now, do you have Python and installed in your laptop? Do you do Python programming, like Jupyter Notebook, Anaconda kind of thing? If it is, we can do simultaneously, because still you don't put your hand in the mud, you don't get the knowledge. But if you've not, then okay, Anushka, then please open your Jupyter Notebook. Jayashree, open. Anubhav, you don't have, no problem. This is just a demo class. When we are doing it, we will do everything together. So when we have regular classes, we'll completely install the Jupyter Anaconda, or if you're using Linux machine according your Windows machine or Apple, and everything that we do over here, you'll have to also code it, because otherwise it's just a story and it may not go inside, but when you practice it yourself, it goes completely in your head. So I have picked a small data. Now I intentionally did it an online source of data, so that we don't have to send it through mail at this point of time. But later we in the class will pick a fixed data and we'll do complete analysis of that data. And for another source of data, you will be doing that by yourself. Okay. So let me see if I can send this link over here. Just copy this, import pandas as PD is the only thing that you need. This portion, import pandas as PD. Can you see my screen, or should I increase the size? Okay, I have increased the size nevertheless. So import pandas as PD and then run this code that I have put it in the chat window. Let me know when you're able to do it. So now this is data, which is a time index data. So you see this data. So whenever you import time data in pandas, so this is, you can just read it from your hard disk, or you can import it directly online, as I'm importing here from this GitHub link. I hope you do have a GitHub account, though we don't need it today's class. The thing that we do is, one of the column in that data is date, and one of the column is that data is value. Now this is a data frame, a pandas data frame kind of thing. Data frame is just like an Excel sheet. So when we do all this, we will have basic knowledge of Python data types. So there's a list, there's a dictionary, there's a tuple, which are all one-dimensional data. Like list is a collection of values which is mutable. Tuple is a collection of values which is immutable. And dictionary is a key value pair kind of values. We will discuss that in a lot of details, but when we come to a data frame, that's a two-dimensional data, something like an Excel sheet, where one column has a particular data type. So we have this date value. This value is, say, just a float number. Then I can have another column which is an integer number, another column which is can be the name of a person, or kind of data. So that way it can go on. But since this is a time indexed data, so here we have values like 1st July 1991, 1st August 1991, 1st September 1991, so on and so forth. Now each of these start of the month has the value like 3.526, 3.180, and so on and so forth. So it can be in some units. Is that okay? So far so good. Now what do we, when we plot a time index data, what does it look like? So let's take two stock markets data. So now Quandle is another application in Python, where you can import stock prices data or any macroeconomic data and see where it has gone through. So this is the General Motors stock price data. See, it starts at around $30 or somewhere, goes up, comes down, and it reaches its minimum in, does it reach its minimum in 2016 or 2014? Since the start of 2011, what do you say? Around what time the stock price of General Motors is at its lowest? I'll keep asking small questions so that I know that you're able to listen on the other side. Otherwise, in case you're cut off, I won't even know. That's correct, Jayashri. Around 2012. Or, this point or this point, this point looks, Anushka, very, very good. This point looks a little lower between 2012 and 13, but both of you correct, it's around 2012. So this is how General Motors price has been going up and down. Now, can you say that any point of time the variation is more than other point of time? Has it been at a higher variation, say in this region in 2015-16 as compared to 2012-13? Does it feel like? That's right, Anubhav, very good, between 2012 and 2013. But is its variability changing? Is the amplitude of the wave changing? Is the frequency of the wave changing? The way it's going up and down, is that changing over time? The mean has changed over time. In this period the mean is really low, in this period it's somewhere in between, and in this period the mean is very high. But is the variability, the variance of the data at any point of time changing based on what you are seeing? Can you say that? Guess you're not able to get. So this magnitude of change, Today the price is at say $25. It goes up $5 in a day, and $5 goes down $5 the next day, and again, $5 again the next day, $4 the next day, and then $5 up, $6 up, and so on and so forth. Jashi says variance is not constant over here. So the change, is if I do normalization, if I normalize the data at any point of time, though you don't do normalization in time series data, the, the change is not changing much. The frequency is not changing much, except here when it moves from, here the mean. So if I take the year 2011 and 12, the mean is around 20. But if I take the year 2013, 14, 15, 16, the mean is around 13. The mean has changed. Everything has shifted up, but if I draw a line over here and over here, the things are moving around those values only. So it is difficult to say whether the variance has the change in the values have changed a lot or not. The variance has definitely changed, you are right, in the sense that if I calculate mathematically, since the mean is higher here, so by that magnitude the variance will go up. But on its own, it's difficult to say that the variance has changed completely. While if you see this graph, this is Tesla stock price. If I take this region from 2010 to 2013, the variance is very low. There's no going up and down and up and down over here. Even if the prices are low over here, it just fluctuates up and down, similar to what is fluctuating over here. But here there is a constant thing. It is not, the variability is very low, the mean is also very low. Here the mean is increasing, but the variability has also increased a lot. Okay, so the mean, there has been a jump over here and then a jump over here. The variance has changed, the mean has changed. Okay, so this is the Tesla stock price, while this is the General Motors stock price. Now what kind of car does Tesla make? Any idea? Or is it trying to make? Battery car and also self-driving car. Okay, so we have got a basic, these are simple stock prices data, and that is as time series data as it can get over here. Macroeconomic data are also time series data. Now here I'm importing data from GitHub, and in Python, just to let you know, I'm doing parse dates over here. Now what does this do? This tells Python that this column is the date column. So when I do data frame, I imported it in this object called data frame, and when I do data frame to data types, d types is the command, then I get the value is a float object since it has decimal points, and this date is a date time. Now all these programming languages, especially in R and Python, they help you handle and even in SQL handle date time objects quite well. Now the Python has already understood that this is a date column, and it has already arranged it accordingly, where the farthest back in time comes first, and so on and so forth. Sometimes there may be a confusion whether this is the month column or this is the day column kind of thing. Then you'll have to clearly specify in the code over here that which comes first. It is YYY by MMDD or DDMM or DDMMYY, and so on and so forth. So that can be a big trouble sometimes. Now you understand what's an index in a data frame or in SQL table? What an index is in a data frame or an SQL table? Do you know? Starts with 0, an index starts with 0. Others are not saying, so I'm assuming that they're not very sure about it. So then in that case, let me tell what's an index. So an index need not start with 0. Index is like, it's a common key, it's a row identifier. Now over here you see date tells you which column I'm talking of. Value tells you which column I'm talking of. I can have more data, index represents data to be searched in a faster way. Index is used like that, but it's not defined like that. Very good answer, Anubhav. So now suppose I have another column. This is the value of the stock price. Next is the volume of the stock price. Next is the dollar rate on that day. Next is the crude prices that day. Okay, these are all those we can have more columns over here. Over here, I want to identify the first row. This is the index over here. This 0 is the first row, 1 is the second row, 2 is the second row. Like when you tell someone, hey, can you look at the row number 232 when someone is looking at the Excel sheet? Column Q, row number 232. So that way, this is column is date, this column is value, and that row number that you're talking of is the index over here. There's a column identifier, there's a row identifier, and that's the index. But the good thing is you can have anything as the index. It not be a sequence of natural numbers starting with 0. I want to make this date as an index because my whole data is time indexed, date indexed. So I want, whenever I do time series analysis, it should automatically say that this entire row is for that day. So you don't have to say, hey, can you go to that column on that Excel sheet? You can just say, hey, can you go and check what was the stock price on in 2002 November 23rd? So then the person will just filter and search on the data frame the stock price for that day. So to do that, instead of just parse date, so whenever you import time series data, these two columns commands you have to always remember. This parse dates is like it will take that column as the date and index column is the date. So I have taken this column as the date column. So now look how my data has changed. Now my index is this date column. Earlier date was just a column in the table in the data frame, while index was the 0, 1, 2, 3, 4. Now the date itself is the index. Now if I do print data frame data types, look how things have changed. Over here I get this date time 64 ns, value float 64. Here there is no date time ns 64 ns, there's just value of float 64. So in time series, the whole data science thing, has multiple aspects. One is understanding the statistics of things. One is being able to code it and handle the data in Pythons. And the other part are business understanding on how to apply it and then how to interact with the business to make them understand it. So let us know, the basic, whenever you have data, the first thing you do is get an understanding of it. Now, if you have volumes and volumes of data, like they say, a picture is worth 1,000 words, so you get an understanding. Now, this data is anti-diabetic drug sales in Australia from 1992 to 2008. Let's plot that data and see what it looks like. I'm just using a PLT style use called 538. This is just the grid behind and it looks better. And then I define this, when we do matplotlib, we'll understand this better. So I have df dot value is the column that I'm selecting. Then I'm plotting that. The color is green, the figure size is 14.5, the font size is 12, line width 3, line types and all that. Then I put it as an object called AX. And then I AX set X label, AX set Y label, AX set title. These are basic, as English as possible. And then I ask plt.show. PLT is matplotlib.pyplot, which I've saved over here as import matplotlib.pyplot as PLT. When we progress in the class, there will be basics class on Python and pandas, and then you'll be moving into time series. So not so many things will be coming at one go. So, one step at a time and the build-up would be better. But since I have to give a overall picture now, so I have to touch different things at the same time. So now look at this graph, such a beautiful graph. What does it tell you? What period are we talking of over here? From when to when? Data is from when to when. What does it look like? So Shiva has made a very good observation. Now, what all can you say about this graph? You were suppose you want to start your own pharmaceutical company based on this anti-diabetic drug in Australia. Say you want to start it in China or in USA. So the first look at this graph. The first thing, okay, this data is from 1992 to 2008. That you have got everyone absolute correct. Now, what else is happening over here? Is it absolutely a random number? Is it that it goes once it reached its peak, then came down like a big mountain and comes down and goes down for all the time? Or a big deep lake goes down, then keeps going up like a mountain? What can you say about this data as a business person? You know, you don't have to be know even basic of mathematics. You just need to know how to sell things. As a business person, what information you are getting from this graph? So most of you have got it. That's right, Gautam. So the consumption has increased over the year. The mean in 1993 is less than the mean in 2005. But one thing that I think Anubhav or Jayashree is pointing out, yeah, Jayashree, is about, there is a seasonality in the data. At the start of the year, is it low or high? And at the end of the year, is it high or low? Can you say that it is moving from something to something every year? The overall consumption has increased, but within a year, in every year, can we say something is happening? So there is a trend in this data that things, my sales have consistently been increasing from 1992 to 2008. Another thing that I can say is that start of the year, the January value is probably low. And as I keep moving from February, March, April till December, it keeps on increasing for every year. Now that is a weird thing. Like, why would anti-diabetes drug have low sales in January and high sales in December for a country like Australia? I don't know. But if I'm the business person who is in the pharmaceutical industry, I would definitely like to know. So you understood? So the coder in you, what does he do? He puts this data in date time format, plots the data, very basic, or makes it a time series data. The statistician in do, what does he do or she do? The statistician looks at the trend, the seasonality, the cyclicity, the randomness, and tries to mathematically break it down, tries to do a prediction. The business person, what does he do or she do? She looks at, oh, this is a drug that has been increasing over here. It will increase, the demand will increase also next year. Let me get into this market. Or if I start this in another market like China or Japan, then where there is no drug, then slowly, I need to see what this company has done to increase the sales. So I will also do that. Okay. And then the manager in this will also ask this question, why is this happening? Or if you are from the hospital industry or the public policy industry or the government health department, that why the drug sales are low in January and high in December. What incentive is resulting in the code? For those who are writing the code simultaneously, please let me know. Okay, so this is just copy paste this first, and you have to also import matplotlib.pyplot as plt input. Now this thing in the first cell of your, okay, Jayant is done, copied these lines of code. Anyone else is coding parallelly? Great. So once you have done that, so let us move on. And this is the last plotting code. I'll just send this to you. Okay, so now the beauty of this data frame is, this time index data frame is you can do a slicing and dicing very easily. So you want to see only data of 2003. So you just write like this, df 2003. And you have all the values for 2003. So there are 12 values for January, February, March, April, May, June. And you see January is actually high. It's not that December that's the highest, it's January among the highest. And from February it drops, then February goes to the bottom, March picks up, April picks up, May better, June again a drop. So every year we see a sudden drop in June from May usually. Then July, August, September, October, November, December. Now suppose I want to see data for 2007. Instead of 2003, I just do 2007 and control enter. Oh, I had shut down my laptop, so just one sec. Let me run this code again. Shiva, are you able to draw the graph? Jayashree? Okay, Jayashree is able to. Shiva is still trying. That's great. And here is the 2007 data. Again in 2007, January is high, dips in February, March increases, April again dips. See, April every year it is dipping. So these are the questions that you should ask, and you should ask the business, and you get a business understanding of the business, better understanding of the business. Now suppose I want to see entire last 2 years data. Any suggestion what we should do? Like we want to see not only of 2007, but from 2007 till the end. To do that, what should I do? If you have basic knowledge of pandas, okay. So these are small things that are really helpful. I just put a colon over here and I do control enter. So now you see I have the entire 2007, entire 2008 data, 2008 June till whatever data I have. That's very correct, Jayashree, very good. So I just put a colon over here and I get this entire data. Great. So we know very basics of how to import data, how to plot that data, time index data, and how to do slicing and dicing of this time index data. Now, like you said, in this data, there is a trend and there is a seasonality. Every year, January, it's high and then suddenly falls in February and slowly keeps on increasing till December. And in between, it usually falls in June and July, and there is some kind of thing that is common over there. But we want to break it mathematically, statistically into those parts. So these time series data can be, broken down into the trend component, this line that is increasing. Then it's seasonality complement, that in June it's different, in July it's different, and so on and so forth. And a cyclicity component which we won't be doing over here, but we'll discuss this later. So here it is, from the stats model API, I have just imported this model, stats model API, and I create this decomposition. In this decomposition from stats model, this time series data is broken into seasonal decompose. Now what I'm breaking, this data frame is what I'm breaking. What kind of model it is? It is an additive model. There are two kinds of model, additive model and multiplicative model. I'll explain that in a moment. And then from that, we draw this figure, decomposition.plot and plt.show. Now this is what it looks like. So if I look here, this is the observed data. This is a smaller graph. So this is the first row that you are seeing is the observed data. It's the same data from 2000 till 2008, whatever we had. Now this blue line, the second one is its trend component. If all these things, like for every year, if I have one value, that is mean of all the months kind of thing, so then that is the trend value. Now this line is fluctuating around this line, the above line is moving around this line. Now how is it moving? Look at the seasonal value. This is the January value. February it really comes down, March it peaks up, April little down, May moves up, June little down, July again moves up, August, so on and so forth, till it reaches high again in December, January of next year, and again it falls in February. So if you put this line on this first line, see the seasonal, look over here, the seasonal on this trend, it will start looking like this. But then there is still a random component, and that is this part. That is called the residual. So if you add the second, third, and fourth row, you will get the first row. Is this clear? Now tell me, based on this data that you have, you are in 2000 and, suppose what's the date? The last value we have is for 2008, suppose we have, okay? Now we are in 2009 and January, and you have in this manufacturing, you manufacture these drugs, okay? So for 2009, you don't have any data for 2009. You have data only till 2008. Now you have to decide for which month will you manufacture the most. Now you're sitting in 2008 and planning for entire 2009. For which month will your production of this drug be highest based on whatever you are seeing? That's correct. So 2019 January and December, my production will be highest. My next question, will your 2009 January production be higher than 2008 January production or lower than 2008 January production? Similarly, June 2009 production, it will be higher than June 2008 production. If you produce too much, what will happen? If you produce, much more than what is required in the market, and medicine does not last all long. Medicine has a shelf life. So if you produce too much than what is required by the market, then there will be very good gesture, there will be a wastage. There's a holding cost, there's manufacturing cost, there's a wastage cost. And if you produce too less, what will happen? There will be a lost sales. Awesome, Jayashree. So some dollar that you could have got, you would not get. People will be unhappy with you and then move to a new company. So based on this data, you don't want to produce too much, you don't want to produce too less. How will you decide? Now, can these three rows help you in figuring out how to decide for each month? And this, believe me, this is actual data. This is not a data that I have created for you or someone has created for to teach time series analysis. This is real world data. So what will you do based on the data that you have over here? You are the production manager, you are the head of or CEO of a company, and you have to decide how much to produce. So based on these three graphs, you have the mathematical data for it. How will you figure out how much to produce? In fact, you don't need any knowledge of mathematics. Suppose this is there on this graph is on paper in front of you and not on a laptop. What will you do as a simple business person, as a layman business person who doesn't understand anything of maths and stats or programming? Very good, Jayashree. So what I will do, I don't know statistics much, I don't know programming much. I'll just take this line and can I draw over here? Yeah, I will just pull this line further. Okay, like this, I will pull this line. Then this same thing, I will extend it a bit more like this and then like this. And this randomness I cannot help. I will come to this randomness later. And I will, so this was 2008, now I'm in 2009. 2009 for a particular month. I will add these three up and get a value. And I will decide that that will be my production amount for that value. Is that clear? Very basics, right? Does not require any knowledge of statistics or machine learning. Actually, all of statistics is very intuitive like that. Everything in stats and in machine learning is as simple as this. There's nothing great happening over here. Just the terms are like that, which makes one feel that, oh my God, what are the people talking? But if once you understand that, they are very, very simple things. Great. So we, we are understanding it better. And I hope you don't think that you are missing out on something, because this is all what time series is. Now, the thing that I told you before, there's additive time series and there's multiplicative time series. What we did above was the additive time series, where you divide the value to a base level plus trend plus seasonality plus error. Okay, so here I could have removed the mean, so I would have got a base level also, but we have not removed the mean, so that is kind of trend and base are combined over here. So base is the mean overall, the trend is this line, this is the seasonality, and this is the residual or error term that it is called. Okay, now instead of additive over here, I could have done multiplicative also. Let's see what that looks like. Multiplicative. Uh-huh. Multiplicative looks also quite similar, isn't it? Now, when to use additive and when to use multiplicative, we will discuss this more in later classes. It's clearly defined. But then there's something called the washing machine approach. There, once we are done with this time series, you will be knowing many different ways to handle time series. And in a project that I did recently, we produce 8,000 per time series predictions for same value. And then we created an algorithm above it and said that, that we call ensemble learning, and that we said that, okay, with time, at this point of time, based on seasonality, in this season, these models do better. In this period of time, these models do better. Over last period of years, these models have been doing better. And based on that, collectively, we've decided that we will be selecting these models at a different time point of time. We created an algorithm for it, and that worked really well in our data. So one thing, there are two different approaches whenever we do such things. One is going step by step, complete statistical understanding. One is just putting everything in a washing machine and seeing whatever comes, and whichever you like the most, you pick that up without understanding what happened behind. So depending how fast the business wants the result, or how much statistical understanding you want or the business wants, one can do a trade-off between the two. Is it like from time to time model we use will change? Very good question, Jayashree. Yes. Over a long period of time, the model that we'll use is changed. Now see over here. This was 2002 to 2008. Here nothing is changing. Over 6 years, 1993 to 2008, 92 to 2008. That's around 16 years, 17 years or so. So in this, the model will not change. But sometimes, competitors will enter the market. The whole diabetes scene has changed in the market. So then my data will tell me that I should use a different model now. So there is a train data and there's a test data. So what we will do over here in this kind of data is, let me take it over here. So now you have this data from here till here. Now how to decide which model to use, say additive or multiplicative? These are the only two models that we know now. But say we have ARIMA models, VAR model, VECM model, um, or some different time series model. So how to figure out which one? So one way is to take this entire data and make a model based on that. But then how do you figure out which one is better than the other? Any guess that, once you have created the model, how do you know which model will be better than the others? Like I said, 8,000 models we created. Performance, very good, Jayashree. But how do you measure that performance? Like suppose you are the business person. I'm the business person. Accuracy, very good. Uh, Shiva has asked the question, in time series modules, will we be using all supervised algorithms at a time to select the best models? Shiva, that thing, that's a very good question. That depends on you. You as a person, how do you decide it? But if something is very obvious that does not make sense here, then we would not use such a model. But some algorithms makes a sense here, and you don't want to spend time analyzing it. You just want because your processing power and memory power is quite cheap now, so you'll just run everything, and you can do that as well. It's a choice that you have to make based on business requirements and speed needed, and how much you understand you want to do doing immediate prescriptive analytics, or you're generally doing a descriptive analytics where the business is trying to understand what is happening, or the business just wants to know what to do next, how much to manufacture. I don't have time. Can you tell me fast? So based on that, you decide. Oh, Jayashree, no problem. So, so can you tell me? So you said performance accuracy. So you must have done basic regression. In basic linear regression, we have this R square, that how much we predicted, how much happened. So that decides whether the model is good or not. Now I give this data to Shiva, and I give this data to Jayashree, and I this data to uh, Gautam, and they come up with models. Now I have to figure out whose model is doing the best. So one thing is I wait, I ask you to give 2009 data. We are in January 2009, and then I do my own manufacturing, and then I see that if I've used your data, what would have happened? Who would have caused me maximum lost sales? Who would have caused me maximum wastage cost? Or who would have cost me the overall sum of maximum wastage or lost calls, and who would have cost me the minimum? So then the measurement, like there is R square in linear regression, there is no R square in time series analysis. Many people say R square of time series. If you go at interview, the interviewer will not ask you the next question also. Okay, so never say R square is there in time series. What is there in time series is called the MAPE, M-A-P-E. That is the performance measure in time series analysis. So how we use it? So we have, suppose, this 2009 data. There is the actual value for January is say 100, February is say 10, March is 20, April is 30, May is 40, June 60, July 65, and so on and so forth till December. Okay, in December is say again 97. Now Shiva has given me some values. Shiva says that this will be 100, and this will be 12, and this will be 13, 14, 15, 16, and so on till I don't know, say 19. And then there is Jayashree. She says this will be 80, and this will be 9, and this will be 21, and this will be 29, and this will be 41, and this will be 59. Now who's giving better accuracy over here? J or S? The second column is J column, the first column is S column. Who is giving a better accuracy over here?
I think J will be the better accuracy.
That's right. Okay. So, but how to do that? There's a thought, but we need to attach a mathematical number to it. How do we attach a mathematical number to it? I'll take the difference. So for S, the difference is 100 minus 100, 0. 10 minus 12 is 12 minus 10 is 2. 20 minus 13 is minus 7. Now this minus and plus will cancel out. So I don't want that to happen. So how should I take care of that? I don't want this minus and plus to cancel out. If someone has made mistakes, lost sales is also bad, and wastage is also bad. Very good. One Jayashree says it should be square. That's what we do in R square in linear regression. But the other, what we do in time series is we take the absolute value. So absolute value of this, so absolute value of minus 7 is 7. So this A in MAPE is the absolute value. E is the error, P is the percentage. So we calculate the percentage, and then we take the mean. So for all these 12 months, we'll take the mean of this absolute percentage error. So we calculate the absolute value, we divide it by this denominator, we calculate the percentage, we take the average of all the 12 months. Okay, so that's what we do. So then at the end of 2009 and say, okay, yeah, J did better than S. So now that's what I should have done. I should have not taken S's advice. I should have taken J's advice. But standing in December 2008, is there something that I can do better than this? I have this MAPE calculation for S and J after 2009. Whole 2009 got wasted. Okay. If I had taken J's advice instead of S, I would have done better. I'm in December 2008. So instead of taking there and deciding that randomly that I'll take Shiva's advice, what else can I do as a business person? What's your guess? If you are the business person, what I will do, I will hide the data. Okay. I will give to both J and S data only till 2007 without giving them data for 2008. Okay. And then I ask them, give me your predictions for 2008. And whatever predictions they give for 2008, I will see who is doing better. Now, if J is doing better, then I will give her the data for till 2008 and ask her to give me predictions till 2009. Have you understood this? Shall I repeat? I can always repeat. Please don't feel shy. So there is called training data and there is called test data. So what I did was I had this entire data till 2008. I am in December 2008. I have data till December 2008. So I split it into training and test data. My training data was till 2007 and my test data was the entire 2008. And to Jesse and Shiva, I gave data till 2007. That was the training data. It was for them to train the model to come with the parameters for the model. And based on those parameters, I got the value for 2008. And I saw, tested it on 2008, who is getting a lower MAPE to decide whose model is better and to use it for future reference. Okay. So that's the term training and testing. You have to keep that in mind. So the term that we have learned in now is additive model, multiplicative model, seasonality, trend, base, error, residuals, cyclicity, MAPE. What does MAPE stand for? Can you write it down? What is the full form for MAPE? Very good, Jayashree. Very good, Shiva. These are the names. Debraj, what's the answer? What's MAPE? Mean absolute percentage error. Okay, that is MAPE. So we know why it's this absolute, why we know it's percentage, why we know error, and why we know it's mean. There's another thing called cross validation and another thing called k-fold cross validation. We won't go in those details now because then we will digress from the topic. When we are doing it in more details, we'll go through those topics as well. But remember what is training data and what is the test train test split and what is train test data. Okay, so we understand what is additive and multiplicative series. Okay, now this is just a diagram that I have drawn, which looks nice for business and all. So keep in mind that whenever you're working with the business, these diagrams are very helpful. So one thing is understanding yourself. The bigger problem in whole this data science industry is to convey it to the business what the model is talking of to get their confidence. So we'll be doing these small things as well to get an answer.
Sir,
Okay.
one thing
So
I just want to ask
yeah.
that how can I decide that when I active or multiplicative model for to measure the performance?
Okay. So like I did the combinations, right? So you can do the same thing over
Yes,
here.
yes.
So if I have this broken, this is into additive and multiplicative. So this is called Holtz-Winters model and Holtz model, and based on that, I'll have predictions for based on additive model, based on multiplicative model. So I'll split the data into 2007 as the train data and 2008 as the test data.
Train data and testing data. Yes.
Yeah. So my train data is till 2007. My test data is for 2008. And I'll build the model
Yes.
for 2007 based on additive model and tested it on 2008
Okay.
and get the MAPE value. Again, I'll build the model for multiplicative as well as additive for 2007 and test it on 2008, and I get the MAPE value and see which one is doing better. But there are, when we do more class in details, when we build this whole thing up, I'll explain that in what case it is obvious that the additive model will work better, and what case multiplicative model will work better. We'll go through all those slides as well. So every time you don't like what is common wisdom, you don't have to reinvent the wheel by yourself. Okay, now this is another real set of data. Okay, this is I'll share the code with you. You can run it yourself. The last one is the air passenger data from 1949 till now. The first two is some other data. So this data, can you tell us, these are all real world data, not created by. So first data starts from 1970, goes on till somewhere in 2010. The second data probably starts in somewhere in 1800s, ends up in 2000 start. The third data starts in 1949 and ends up in uh, somewhere in 1970. So can you say some basic things about this data? Suppose these are sales of three different kinds of drugs in three different kinds of markets over three different periods of time. Very good. First graph, constant increase in trend. So first graph is, like a vitamin tablets that people have started using and has gone. Second is, very good, Shiva. Second is according with season, in the rainy season, or in the winters, people get common cold. So the demand for common cold, the paracetamol tablets is highest in winter. In summer, there is no requirement. And the last one is what we have done before, like the diabetes tablet. There is a trend, there is a seasonality, there's no cyclicity. Okay. Third depends according to season and type of drug. Season and trend, not type of drug. Very good. Okay. So that's perfectly right. Now there's something called stationarity in time in statistics, not just time series, in statistics. So when we do classes, we do what is different moments of data. Do you know what are different moments of data? The first moment, the second moment, the third moment, and so on and so forth. And how are they calculated? In statistics, simple statistics, I assume you don't know. Okay, so we'll be doing that. So basically, first moment is the expected value, and it is called the mean of the data. The second moment is the expected value of the data square, and that helps us in finding out the variance of the data. Variance is not the second moment of the data. Second moment of the data helps in finding the variance. The third moment is the expected value of the cube of the data minus the mean, like x minus mu the whole cube, it's expectation. So we'll do whole expectations and all later. That helps in finding the skewness. The fourth moment helps in finding the kurtosis and so on and so forth. When we are doing uh, uh, data analysis and it's all these moments are not changing over time, then it is called a strongly stationary data. But if any of them is changing over time, if the mean is changing over time, if the variance is changing over time, if the skewness is changing over time, the kurtosis is changing over time, if the covariance is changing over time, then the data is no more stationary. The problem is mathematically it's very difficult to prove whether the data is strongly stationary or not. It's very easy, when you want to prove something is wrong, if you just take one point and say that here it fails, then you can say all about it is wrong. Okay. Yeah, so Shiva knows what's first one and second. That's great. But if you have to prove something is right, and there are millions of possibility, even if you have shown in 100,000 cases that it is right, there may be some case where it may be wrong and you don't know about it. So in that case, in statistics, especially for time series, we define something called the weak stationarity. Weak stationarity is that the mean remains same over time, and the covariance remains same over time. So you understand what is variance? So variance is, you understand what is mean? I assume you understand what is variance. I hope you also understand what is covariance. Now covariance over here is with time lag. So the value today and its variance with the covariance that I'm talking with time lag 3. So value today and 3 time periods back, I take all those values and I calculate the variance with respect to the covariance with respect to those two columns, and we get the covariance. Is that clear, or shall I write it on the screen how to calculate covariance? Once I start interacting with you, I'll know better, at what level to pitch. But since it's the first class, so you'll have to give me cues, at what level I have to go. I don't want to be fast. I don't want to bore you with details as well. It's clear. Okay, fine. So, so you understand how to calculate covariance. So, weak stationarity is what we'll be dealing with. And whenever we say stationarity, what we're talking of is weak stationarity. Weak stationarity means the mean remains same over same and the covariance remains same over the same. If covariance is same, then variance will also remain same. Now, in this first case, this trend only graph, can you say that the mean has remained same over the years? Very good. It has not remained the same over here. In the second case, can you say the mean has remained kind of same over the year? Not exactly, but roughly, if in 1950s, if these peaks are removed, can you say the mean has remained the same over the years? Suppose these peaks are removed. Kind of, it has remained same. Very good, Arif. But has the variance remained the same over the year? Shiva, you're right, not completely, but for the benefit of the teacher trying to explain.
Sometimes,
Yeah,
sometimes the
please.
peaks are high, so the variance are maybe different.
Yeah, so the variance has changed over the year, but the mean has remained same. And in the third case, both the mean and the variance has changed. Okay, is that clear? So, is any of this data weekly stationary? Any of these three data weekly stationary?
No.
No. Very good. None of them are weekly stationary. So first we have to convert the data into stationary data, and then we can use models like ARIMA models to do the prediction. Okay. So what is stationarity? We have to understood. How to test for stationarity, we will discuss towards the we'll come to that in very soon. Non-stationary and weekly stationary, we have understood, not constant in mean, blah blah blah. Now so how to remove if the data is not stationary in mean. So in this case, the first case at least, if I subtract mean from the data, then what will happen? If I just rotate this line by a certain degrees, so it will become a horizontal line. That I can do by subtracting some value from the data and then bringing back the trend over here. So this is what, if it's a deterministic trend, okay, then we do something called detrending. Okay, so we take the y value. So all this time index data, y subscript t, because this is a time series data, it will always have subscript as t, and there is a mu, at where it starts or somewhere in between, plus beta times the trend. So which time it is increasing. So this is basically a coefficient of beta over here, coefficient of time, time period 1, time period 2. So there's a constant slope over here, isn't it? If this was not a time index data, I would have just drawn like this, and it almost passes through 0. So this is nothing but y equal to beta x from coordinate geometry, if you remember. Instead of this, if it was from here, then that would become, the slope remains the same, but the intercept have changed. So y equal to beta x plus a constant mu. Okay, but over here there is something, little bit of up and down along this line, up and down, up and down. I'm doing it cyclicity, but suppose it was random. Okay, then that is the error component. So The values over here, this mu is the intercept part, this beta is the slope part, and this error is the randomness along this line. Is that clear? So, but in this case, when you're doing time series data, x becomes time. X is time. So our equation becomes y equal to mu plus beta times t plus the error component. So this is simple coordinate geometry and nothing else than what we did in class 11 or so. So then we can plot this graph and do the predictions over here. As simple as that. Clear? And then when we have this value and we subtract it from that, that will become a horizontal line. If I subtract, this line is giving me this distance, this distance, this distance. So whatever this error remains, if I subtract this line from these values, what will remain is, suppose my line was like that, and let me draw a seasonality thing. So the values are like that along this line. Now when I subtract this y minus mu plus bt, this line will become like this, and this whole error thing will be like the seasonality thing will be like this. Okay, so this trend has been detrended by doing this. Is this clear? That is what we do in detrending. This is what this equation is over here. Yt is mu plus bt error term. So error term is this, and that is what we'll do our on this error term, assuming there is no seasonality. We will do our time series prediction on that. No response is probably a good response. Clear. Great. So that was detrending, and then there is something called differencing. Okay. So what happens in differencing? So I will again take some data and do it. Give me a moment, please. Now suppose I have data like this. January was 10, February was 20, March was 30, April 40, May 50, June 60, September 70, and so on and so forth till December 120. If I plot this graph, what will it look like? Will it have trend? Will it be a straight line? Will it be circular? Will it be random? Will it be zigzag? What will it look like? I've got only one answer. It will be a straight line, but it will also have a trend. The line will look like this. It starts at 10. So this is 10, and the slope is, I think, 2 minus 1 minus 2. Slope is 1 unit. Okay, so it's a 45-degree line. So it goes like that, increasing straight line. Okay, so one way to detrend is this. What is the difference of these two values? 20 minus 10 is 10. 30 minus 20 is 10. 40 minus 30 is 10. Okay, 50 minus 40 is 10. I take the difference of all these values and I plot it. What will that look like? It will be a line parallel to x-axis. Very good. So that will become this line. Okay, so is it detrended now? Does this line have trend or no? It is detrended now. Is it stationary now? Is it weakly stationary now? This straight line? Is the mean same throughout the period? Is the variance same throughout the period? In fact, what is the variance? What is the mean for this blue line? What is the mean for this blue line? What is the variance for this blue line? That's a very simple question. Am I audible? What is the mean for this blue line? And what is the variance for this blue line? These are the values. First value is 10, second value is 10, third value is 10, 12th value is 10. All the values are 10. So what will be the mean and what will be the variance? Mean is 100, 10, correct, very good. Mean is 10. Others, and what is the variance? Very good. Variance is 0, nothing is changing. There's no variability. So what will be a prediction for the next value? For this blue line, it's very simple. Next value is 10, next value is 10, next value is 10. You keep adding those 10 back here. So for January, it will be 130. Next year, February 140, March 150, and so forth. So you do prediction for this line and you add back those values to get the final prediction for this brown line. Is that clear, students? Great. So I hope you're getting a hang of it. So that is simply done in, I did it in Python. So what I did, I imported another data. This is the, which one? The first one over here. The first graph that we have over here. And I take the shift operator, it's called in pandas. So if you see this value 0.31, what was for January 1970, this value has become the same for January 71. This value has shifted here. Okay, one value shift. This one has shifted here. Okay, this one has shifted here. So one previous value I have shifted. If I want to shift the one later value, I'll do -1 over here. And then I take the difference between these two to get this value. I take the difference between these two to get this value. Difference between these two to get this value. Okay, so it's like what I'd written. This was 10, 20, 30, 40, and now this is 10, 20 minus 10, 30 minus 20, 40 minus 30, all 10 over here, and then I plot those 10. So see, this was going up, and suddenly someone has, like, held it by both the hands and rotated it around the center to become like this horizontal kind of thing. Clear? The differencing also helps making it data stationary. If you difference it only once, it's called first order differencing. If you have to difference it twice, then it's called second order differencing. So if there is just a trend, then first order differencing works. Usually for seasonality, we need second order differencing. Is that fine? So differencing, and usually for all the data, by second order differencing, it achieves stationarity for 99% of the data. In very rare cases, I have never experienced a third order differencing, and I have never experienced third or more. No. I'm not saying there are only 2 orders of differencing. There can be 10 orders of differencing, 1,000 orders of differencing. You can keep doing. So let me do another example. I'm going a little slow. I hope that's okay with you, because it's better you understand than I finish everything. So now suppose that was 10, 10. I'm going the other way around. So my differencing should give me this, and I start over here. So this was my January data, 10, 20, 30, 40, and 50. Suppose this was 100, and this was 110, 130, 160, 200, and 250. Okay, and one more order I'll just do so that you understand it better. Choose pen. What should I use? Suppose this was 500, so this becomes 600, this becomes 710, this becomes 840, this becomes 1000, and this becomes 1200, and this becomes 1250. Now suppose this was my data. Okay, This guy is over here, this green fellows, 520 and 500, 600, 710, 840, 1000, 1200 and 1250. Now if I differentiate once, 600 minus 500 is 100, 700 minus 600 is 110, and so on and so forth. That is not stationary. So this is first order differencing, I1. Okay. This is second order differencing. That gives me 10, 20, 30, 40, 50. D equal to 2. D was 1 over here. D differencing 1, differencing 2. And when I do third order differencing, I get this constant values of 10, 10, 10, 10, 10. Okay. To achieve stationarity, I had to do 3 orders of differencing. Is that clear? Gautam, Shiva, Jayashree? Okay, I'll come to explain the difference between, very good question, stochastic and deterministic trend. I'll come to that later. But is this clear? The first order differencing, the second order differencing, the third order differencing. Great. Okay, that was a mistake. So this differencing is clear. So I'll erase this. So when we have data that becomes stationary with uh, one order of differencing, then it is called integrated of order 1, I1. When we have data that can be made stationary by 2 orders of differencing when d equal to 2, we call it integrated of order 2, I2. When it can be made stationary by third level of d equal to 3, then it is called integrated of order 3. Okay, so this should become part of your vocabulary. So I had a very good question in between. What is the difference between stochastic and deterministic trend? Okay, now the straight line is a deterministic trend. But then when you have complete randomness, there is an increase, but complete randomness, then that becomes a stochastic trend. So I'll just draw one. Stochastic means which involves a lot of probability. You're not sure, but it is different from seasonality added or randomness added. There is some logic to it. So it's going like this and like this and like this and like this and like this. So this becomes not. This still has a deterministic trend. This straight line like this, but it should not be so clear. If it is not so clear, then it is not a deterministic trend. It's a stochastic trend. Thank you. Have a great day or night and great learning.